Wonderful. Hey, hello everybody. Welcome to Inside the Memory of SQL at SQLDay. I'm Bob Ward from Microsoft. I actually live in the United States in a great state called Texas. Maybe you've heard of it. And indeed, the way we say welcome in Texas is howdy. So now all of you have been taught how to say hello in Texan. You can just say howdy to somebody and they'll know you're from Texas. So thank you so much for being here today and going through this presentation. We have about an hour to go through. I have a lot of material to go through, a lot of material. This is a very advanced session. I hope that this session was categorized as an advanced session, but I think you'll enjoy it. We're going to see some stuff today that in some cases you perhaps have not seen before. So I just want to make sure one thing that you know from the very beginning. You're probably wondering, how do I get the slide deck? How do I get the demos that Bob is going to do? I will give you all of that. Right now on your screen, you see aka.ms, Bob Ward MS. That is the location where this slide deck is currently already there. So if you're online right now, you could go to that website and look at a folder called Inside the Memory of SQL, and you would find this slide deck. It's already there. You are free to take this deck and present it yourself or reuse it in any form you would like. At the end of the presentation, I have a resources slide where I will give you a pointer to where the demonstrations are that I'm showing you today. So with that said, let's get started on the topic that we're going to talk about. We're going to talk about the architecture of the memory of SQL. And by the way, that applies to SQL Server on Windows, SQL Server on Linux, and Azure SQL. In fact, you can see here that I'm going to talk not just about the architecture, I'm going to talk about certain configuration choices that you're going to make and what I call the term memory accounting. We're going to explore how dynamic memory management works, a very important understanding and topic. I have other memory topics that I'll be covering about things like NUMA, etc. And then I thought it was important that if you're somebody who's a Linux user or a containers user, you can learn more about how that works. And then finally, we'll end by looking at Azure SQL and some of the differences that exist with Azure SQL. Now, I'm new to this platform, so I understand it's possible that you may have questions. So I think the proper way for you is to raise your hand. I will see that here in the Avatar Land application, and we'll stop and we'll answer your question. I may not be able to understand your question in English, so if you want to use the chat as well to type it in, that might be helpful to me as well. If I determine, though, that it's taking too long to answer your question, we may have to proceed to make sure we finish with all the material today, but I assure you, I will give you my email address. Anybody can reach me after the fact if necessary I want everybody to have their questions answered without leaving this talk or at some point after the talk. Okay, so let's dig in and let's talk about the architecture of SQL Server. This is the SQL Server process. It's important to understand a few major components of the memory architecture of SQL. Number one, and you've seen some of these terms maybe before if you've used SQL Server, we have caches in SQL. Caches for database pages, we call it the buffer pool or B pool. We have caches for plans like procedure plans and ad hoc queries, and a range of other caches and pools, including column store. Now, why is it important that I segment out in our architecture that these are caches? That's because these caches can grow and shrink depending on the needs of memory and memory pressure, and they have what's called a backing store. What I mean by that is we can take any of these caches and we can store the data in there on disk. For example, as you know, the buffer pool has database pages, and those pages could be written to a file representing plan cache, for example. Their backing store is system tables, etc. Now, there's a smaller portion of, and by the way, that takes up a great deal of the memory of SQL Server. There's a smaller portion of memory called fixed memory, and they can grow and shrink when they're not used, but in some cases, that memory can never be shrunk. We use something called a memory object for a lot of these things, and there's no backing store. For example, connection memory, memory to support connections, we can't page that to disk somehow, or memory grants. So as it turns out, if your memory pressure is really heavy on SQL Server or you lower things in SQL configuration, you can cause problems because we don't have enough fixed memory to support what you're trying to do, like connect to SQL Server. Now, two other types of memory that are important to know is SQL Server overhead, things like thread stacks. So SQL Server is a Windows process, or even in Linux, a Windows process on Linux. So there's a small amount of overhead required to run the process of SQL that has nothing to do with SQL memory management. It's just part of being a process on Windows or Linux. And then finally, you may have heard of Hackathon or in-memory OTP. It can potentially, if you use it, take up a significant amount of memory, and it can grow, but there are limits to how it can grow. But here's what's really important. It can't shrink if there's data in it. The only way to shrink Hackathon memory is to delete the data, because remember, it's called in-memory. So there is a backing store for Hackathon, but you're not allowed to actually shrink it if somebody's actively using the data in it. So with that architecture in mind, it's really important to talk about some of the configuration choices you're going to make. And I really also want to cover this concept of what does it mean to use paging with SQL Server. One other last point. You're going to see, and we'll show it a little bit today in our demonstrations, you're going to see a concept in SQL Server memory called a memory clerk. A memory clerk is a category or a type of memory. So as you're looking to see what types of memory is out there, like how much memory is the buffer pool or a plan cache or Hackathon or column store or other types of memories, you're going to use a concept called a clerk to see how much memory is made up of a given category. Okay, so super important concept because there's a myth around how paging works with SQL Server and operating systems. So knowing what I just told you about caches, SQL Server can do its own paging as necessary. For example, buffer pool database pages can be written to database files if they're dirty. Like if you change the page and we need to reclaim that memory, we can simply flush the page to disk that's dirty and we can reuse that page in memory. Plan cache pages can just be freed up. We call that plan cache eviction. And if necessary, just reloaded from system tables and recompiled. Or of course, if it's an ad hoc query, the next time the query is run, it'll just be compiled and put into memory. But some memory is not pageable. Within the SQL Server process, we mentioned that fixed memory, like connection memory, memory grants, other types of memory that are needed for the execution of SQL Server. Now that's SQL, how it does its own paging within its own system. What is confusing to many people is that Windows as an operating system, or SQL running on Linux as well, it can page out process memory, including the memory that is for SQL for caches and everything else, including fixed memory. Now, what is the difference there? Number one, the operating system can take the pages in the operating system that represent the process memory and write it to a page file. This is often called a working set trim operation. But look at the bold point here. SQL still thinks all the memory is there in RAM. It doesn't know this has happened. Now, technically, we've written code to observe when this working set type of thing occurs and take necessary steps to reduce our memory footprint. But from a process point of view, no process knows it's getting paged out to disk. And look at that fourth point. It could be the thread stacks for SQL Server that could get trimmed. That is a severe problem because SQL thinks it's all in memory, and the symptoms to you are not within the SQL DMVs or processes. It doesn't know that it has been written out to disk because it's not a SQL paging operation. It's a Windows paging operation. And how would you normally see this? You would see things like process working set or memory pages out per second. You would observe those counters to see whether working set got trimmed. Now, what we're going to talk about in a second, though, is the fact that you can configure SQL Server so you avoid any problems or most problems from a working set trim operation. Okay, now, let's talk about those memory configuration decisions. First of all, it starts with something called a memory model. The default memory model for SQL Server is called conventional, and we use the virtual alloc APIs to do that. When you use conventional memory, your working set represents the most memory of SQL. It's going to be high. It's going to be very comparable to the amount of memory that SQL is using. Locked pages are something that are available to SQL Server if you're using Standard or Enterprise Edition or Developer Edition. And the locked pages in-memory privilege is set for the account for SQL Server. If we detect that, we will use what's called the AWE APIs. And what's interesting there is most of the memory configured by SQL is not part of the working set. Therefore, that memory can't be trimmed by the operating system. This is a technique to avoid working set trim problems. Another less used option is called the large page model, and that is enabled by using this trace flag 834. And in that case, the virtual alloc API call with this option called mem large pages is used. Large pages is used sometimes for very rare cases for high performance scenarios, but there can be problems. Why? We allocate all the memory up front for what we call the target. We'll talk about target in a second. Now, what we've seen is we've observed with column store, there are problems with large pages using that trace flag. So instead, what we recommend with column store is use this trace flag 876, and we'll only allocate large pages for column store. Now, having said that, what about this concept called max server memory? That's another configuration option that you can use with SQL Server. What does it zero mean? Zero means dynamic. Well, here's what it means. It means the minimum, here's a formula for you, of 95% of what SQL thinks is physical RAM. By the way, in a virtual machine, the virtualization software presents SQL as virtual RAM. This is the amount of memory you get. Or 50% of available RAM, okay? So it's the minimum of these numbers. So typically when you set it to 0, you will see SQL use almost all of physical RAM, but not quite all. You can see it's 95%, right? What will happen here is if you look here, the ceiling to which SQL will not grow above is called the target. So max server memory of 0 means that the target won't get higher than those numbers that I listed right there, okay? Many choose to set max server memory to not be 0, but to be a number, a fixed number, but less than physical RAM, especially if they use this locked pages concept, all right? Now, if you do that, if you set the target using max server memory to your own fixed number, we will not grow ever above that number. SQL itself will not use its memory to grow above that number. If the memory grew above that number, that would be like a memory leak from some external process, some DLL running in SQL or something of that nature. Now, here's the interesting point. External memory pressure, which is pressure outside the SQL process, let's say you ran a program on Windows that chewed up a lot of memory, that may cause us to lower the ceiling or the target dynamically, but it doesn't change your configuration. So once that pressure goes away, we could bring that ceiling back up. So remember, target is the ceiling of which SQL will not grow, but it could be lowered based on pressure. Now, what about min server memory? Min server memory is the floor. Think of that as the floor of a building, right? Ceiling and floor, to which SQL will not shrink below. So if there's memory pressure and we start lowering that target, we will never lower the target below the floor. Makes sense, like in a building or an office, right? We don't allocate this minimum at startup, and there's a default value for it. Many people try to go think they should set these values to be the same, and I don't recommend you do that unless you're running like on a multi-instance scenario, okay? And in fact, speaking of multiple instances, here's a very important point. Multiple instances of SQL don't talk to each other. They don't know these values that are set to each other, which is why in a multi-instance scenario, many people do manipulate these values to ensure certain instances get a certain amount of memory. But if you have to worry about min server memory, you must be worried that there's some other memory consumer. Let's say you have a single instance of SQL in your VM or in your machine. If you have to worry about min server memory, it must mean you've got some severe memory pressure going on within the operating system outside of SQL. So unless you're in a multi-instance scenario, you shouldn't need to set min server memory. Okay, let me stop and see if there's any questions at this point about what I've talked about. Okay, we're fixing to get a little more advanced. So let's talk more about the locked concept, because a lot of people have confusion about what does locked really mean. So first of all, with the locked pages memory model, SQL server is locking its memory allocation for all that stuff I talked about, fixed memory, caches, etc., so that Windows won't page it out. And the only way a process, it's not just SQL, it's any Windows process, is allowed to do this is if it has this privilege set for the account itself. If you think you should be using the locked memory model, which I recommend, by the way, on production servers, and it's not working, it's because this privilege was not set up correctly. And again, it's not part of the process working set. So when you look at the working set counters or in Task Manager, you won't see this. Other memory like stacks and heaps and threads and so forth, they can be trimmed. So if there's a severe memory pressure scenario causing working trimmed, then you could see that, which could cause some performance problems because we need to access that memory. Now, large pages is also locked. In other words, if you're going to use large pages for that trace flag, you must also have this locked pages memory privilege set, and that large page memory is also considered locked. Now, here's the part that's a little bit confusing. When you use the conventional memory model, in other words, you don't have this privilege, you may have this privilege set, but we don't use conventional. We may use some locked memory. It's possible. I'm going to show you a technique where you can actually force SQL to not use the locked memory model. Okay, what about SQL memory being locked? Like, what do I mean by SQL memory being locked? So independent of the locked memory model, even if you're using conventional memory model, remember that the max server memory is our ceiling to grow. And memory pressure could cause us to lower the ceiling. So here's the point. If you use min server memory, you are forcing SQL Server to never get rid of that memory, even if Windows, forget about working set trim. So a min is a floor and a max is a ceiling. You are effectively locking memory by setting the min server memory to a higher value, because SQL will never try to get rid of the memory below the minimum. Again, think of a floor, or think of the building we're in right now virtually, right? You got a floor, you got a ceiling and a floor. The ceiling could come down, but all of you in the audience are effectively the min server memory. We're never going to lower the floor to crush you on the head, right? So if I set the min to be halfway up the room, I will never lower the ceiling below that floor. So that's how you lock SQL memory, but that's independent of the locked memory model. Okay, let's look at a visualization of how dynamic memory management works, and then I'm going to show you a demo in a second of what this looks like. So I want to point out a couple of things to you. This is like an example perfmon chart. So first of all, total server memory right after startup is the amount of memory that SQL Server is using, regardless of the memory model that's being picked. You can see here in this case, it's around 500 megabytes or so, right? So that's the black line. You can see here that the target or the ceiling is set to 1 gig. I fixed it using max server memory to 1 gig. Notice that at startup, we do not allocate the max server memory. In large page memory model, we would do that. That total would be up there near that ceiling value. Then what happens what? Let's say you start running a query and we start loading pages into cache from disk. You see here the black line will start rising, but notice that we hit the ceiling. We're right near it. That is called internal pressure. In other words, SQL Server is recognizing I can't go above the ceiling, so I've hit internal pressure. So what's going to happen? This query is still running and needs pages. What's going to happen is that the query, we will start taking pages that we've already loaded and we'll free those up and reuse them for other queries. So performance may not be all that great because we still need pages. Now, let's say you have external memory pressure. Let me go back up for a second to make sure we're clear on this. This is internal pressure. Your total memory is getting near the red line. This is the ceiling. In fact, I'll do it this way to show you. So your black line is near the red line. So that's internal pressure. But let's say there's external memory pressure. In other words, there's memory being allocated in the operating system outside of SQL that Windows is telling SQL, I'm running out of memory. So notice here in this case, the red line drops down to here. And the minimum was 512 meg. That's the floor I set in this example. So the red line will not go below that. But notice the total and the target are now the same, effectively. Now, look here, the query is still running in this example of external memory pressure. So again, we're bringing pages in and out of cache. We call this cache sloshing. That's a term that you may see, and you'll see like page life expectancy go way down because of this scenario. Now, let's say the query finishes at this point right here. But let's say that the external memory pressure is now gone. So notice that the target goes back up to the 1 gig level. But notice that the total does not. Why doesn't the total go back up immediately? That's because I'm not running a query that needs memory. In other words, if I have to lower my ceiling and I have to deallocate memory to get down to that floor, when the ceiling goes back up, I'm not going to raise my total back up to the ceiling unless I need memory. So if another query kicked in, that black line could go back up to that red line. Okay, now let's take a little visualization look at accounting here. Let me see something right here. Let me get this. See. Yeah. Okay, we're going to do a little look at accounting and we're going to do a demonstration. Okay, so you might have seen Task Manager in Windows before. Notice here, I've got columns for working set and commit size for the SQL process. And you might have seen this DMV called DMOS process memory. How do these reconcile with each other? This is a case where the locked model is being used, locked pages. So first of all, the physical memory in use column is a combination of the working set plus locked pages plus large pages. So in this case, the locked page privilege is being set and large pages is getting used at a smaller level. We'll use some large pages even if we don't use it for buffer pool, but locked pages is mainly where the allocations are coming from. So if you're looking at this column and wondering, hey, these two don't line up to this sum, it's because there is some working set memory. Remember I mentioned there's this fixed memory, there's this overhead, thread stacks, all this kind of type stuff. So the combination of these three will be that value in the locked model. But notice the commit size is the same here. So the total commit size of the process from a virtual memory point of view, you see how those numbers line up. Now, and that's why I mentioned about large pages. Even without those trace flags, we can use a small amount of large pages. So what you'll see here if you're using SQL Server is this will remain pretty low after startup, but this will get really high, because the buffer pool will be coming from here and all the caches will come from this value. And this will raise as this is raising up. Okay, now what about DBCC memory status? That's another thing that people sometimes look at. And notice here that you can see the locked pages come from here, the large pages come from here. And so these values do line up with what is in this DBCC command. In addition, there's another command, there's another DMV called OSSYSINFO. And notice here we have committed and committed target. And this is where I know it gets confusing for everybody, like how do I line all this stuff up? Well, first of all, if you can see here, current committed lines up with committed KB and target lines here. Target again is the ceiling. Notice that the ceiling is much higher than the current because we haven't used the memory yet. And then what about perfmon? Well, we make it even more confusing. The target does kind of line up with the terminology here, but notice that total server memory is equal to committed. So current committed is committed KB is total memory. Target is the same value across. Now you're looking at this going, how do I put this stuff together? Notice here that the physical memory here is about what, 207 meg. But the total memory for SQL is only 166 megabytes. Where's the difference? What's the difference? It's the working set at this point, which is all the thread stacks. In other words, SQL Server's memory consumption on how it accounts for memory is not the full amount of memory, but as SQL Server's memory increases, it will become the majority of the memory being used. So when you're looking at accounting information, this working set in the locked model will stay really low, and this number here, total, will get really high as SQL uses buffer pool, plan cache, and other types of caches. So let's take a second and spend some time looking at a demonstration of this so you can kind of put it all together. Okay, so let me go over here. Let me exit this because I want to also bring up Task Manager. Whoops. How do I get a Task Manager here? A Task Manager. So I'm going to bring up several things and I'll walk slowly through you this information. So let's get to SQL Server here. Okay, now I've started SQL Server right now, and you'll notice for SQL Server, I'm gonna blow this up here. Here is the working set for SQL Server, and it's not all that high, okay? It's around 80 megabytes for the working set and that's because I'm using this locked page model. So let's go look at the different SQL commands to see how this all works. So let's go bring up let me bring up perfmon first. Oh, okay, whoops. Okay, this is Performance Monitor. Let's look at a couple of things. Notice here that the target is around 10 gigabytes. You can see that target right here. 10 gigabytes is the target. That's this red line, that's the ceiling. The total is about 500 megabytes. That's the green line right here. But notice that private bytes is slightly above it. Notice that private bytes, and that was in the diagram I showed earlier, private bytes is just slightly above it. That's again accounting for those thread stacks and various other pieces of memory that are not part of the SQL Memory Manager. Now, let's go over and look at Management Studio and look at a few things. Now, again, all these queries are available to you. And I'm going to first look at this output to see that I'm using the locked page model. And then notice here, this is interesting, the target and the committed, that lines up to target memory and total SQL Server memory. And again, the total's much lower than the ceiling at this point because I haven't used any memory. Let's go look at this one. Okay, now what's this? Remember, this is that physical memory in use. So this is going to be locked pages plus the working set are together going to end up being that counter. But you're going to see that going to get a lot higher here as we run queries. And then finally, you want to see this one. These are the clerks that we talked about. Notice the clerks have names. And this, by the way, this clerk here stands for some heckaton memory, but I haven't used much right now. But notice the buffer pool is really low. But if you want to find out what's my biggest memory consumer, you would look at this clerk DMV to scroll through and find out what it looks like. Okay, so now let's do this. Let's go run a query. I've got a query here with a large table, and let's observe what happens. So I'm going to run this query here. I'm going to go look at perfmon. Now you can see in the perfmon graph, can you see that total server memory here and private bytes are going up, but notice the ceiling is still way up here. The reason why that is because I didn't use enough memory that required the ceiling to be lowered. So how does the ceiling get lowered? Let's do it, instead of causing external memory pressure, let's artificially lower it. And the way we do that is we're going to use max server memory and we're going to lower it to this value right here. Now I want you to observe what happens when I do it. Notice it immediately does not go down. But watch in a second, it'll go down. Ah, it went down. Now do you see that? The reason is that whenever you set max server memory dynamically, background processes like LazyWriter observe that and they lower the ceiling down. Now notice that SQL did not have to reduce its memory usage any, right? Because the ceiling or the target is right above, or the ceiling is right above the total amount of memory. So I didn't have to trim anything here. But what if I did this? Let's go here. What if I remove down the ceiling to a gigabyte? Now let's see what happens. I expect the green line to go down. And you'll see it happen. Boom. See that going on? See, now the green line's going way down. SQL is giving away memory. We're deallocating memory from the operating system. And because it's cached like the buffer pool, it's no problem. We can just give that memory up. It doesn't matter. If the pages were dirty, they had been written to, we'd have to write them to disk. Notice now that the ceiling and the total are about the same, and the private bytes are a little above that, which is all those thread stack information. So you can see now, this is artificial memory pressure or internal memory pressure because I'm controlling SQL to do it. External pressure would be if another process ran and caused us to go down. Now, one other thing to do, let's go set the ceiling back up. Let's do that, and let's go see what happens. Oh, look at that. Now the ceiling is back up here, but notice that the total stays here. Why is that? Because we haven't used any memory yet. So we brought our ceiling back up. Okay, this is dynamic memory management, but we don't need the memory yet. But what will happen is if I go run this query again, you will see it grow back up. See, there we go, dynamic memory. It's so funny. You'll find this a very interesting story. In the early days of SQL Server, I worked in technical support. I remember being there at your conference in 2014 as a member of the support staff speaking to you. And in those early days, the Windows support team used to call me all the time and say, hey, I've got another customer with a memory leak of SQL Server. And they would show me this chart just like this. And I'm like, no, that's normal. SQL Server will use as much memory as the ceiling is set to, which could be 0, right? Could be the physical memory. And we will grow until there's pressure. So we had to teach our own Windows team in the early days, this is the normal behavior for a SQL Server. All right, so let me go back, and I'm going to set this back to its normal values. And let's do something really advanced now. We are going to use the debugger. I know, you're like, debugger? What? So I've got a little file. This README file right here is in your instructions, but I'm going to use this over here as part of my use of the debugger. Now, how's this going to work? What I'm going to do is I'm going to first restart SQL Server. Okay. So let me do this, just so I can kind of see the avatar here, what's going on. Okay. I'm going to restart SQL Server. What I'm going to do is I'm going to stop it and restart it because I want to get back to a fresh cache so I can show you some things, all right? So let's go and back and start it again. Now, here's what we're going to do. We are going to run the debugger. And the Windows debugger is going to allow us to attach to the SQL process and go look at some behavior of how memory works. So I'm going to run this. By the way, I have this in the instructions right here. Do not try this on a production server because you will stop your SQL server. So, sometimes I have to remind people this is just for development and testing purposes. Okay, so I've stopped the debugger, and what I'm going to do is I'm going to set a breakpoint on the code for this right here. This is the AW APIs. So I'm going to stop it, and then what I'm going to do is I'm going to go run a query to see what happens. Oh, I already hit one. But I'm going to go run my, let me go hit go here. Let me go run my query to see what happens. Let me go back over the debugger, and I've hit a breakpoint. Now, what does it look like from a code point of view as we're allocating memory? I'll show what this looks like here. This is an example of a parallel query right here, okay? And it's doing a scan of a table. So as you go up the chain here, what's happening is this. This is doing a read ahead in the buffer pool. So what we're doing is we're going to disk and we're reading in pages and pulling them into cache. But we don't have enough memory allocated in SQL Server to support the cache. So what we do is we call one of these memory clerk programs in SQL to say, give me some memory. And if you go up further here, notice this line right here. This is the lowest levels of SQL OS. You may have heard that term before, SQL OS. This is the SQL OS code right here. Sorry, let me get this back here. Telling me I need some memory. And this is the Windows API to get the memory. This is an example of allocating memory dynamically in SQL that is not part of the working set, okay? So if I go ahead and disable this breakpoint, let's go look and see what happens. Because I'm going to let the query finish. And when I do that, let's go look at the accounting that we showed you earlier. So notice here now, I'm using locked pages. My target and my commit look almost the same, but look at Task Manager. Let me get that up here. The working set for SQL Server is still low. Notice it's only 150 meg. I'm using 4 gig of memory, but only 150 meg come from the working set. This is why it's not trimmable, okay? Now looking back over here, I can also go look at these other counters I showed you before. Notice that most of the memory for this come from locked pages, okay? And even I can go look at the clerks I showed you earlier, and now you can see here the buffer pool dominates the category of memory that I'm using. Okay, so that is an example of locked pages of memory. Let's have some fun here. Let's go force SQL Server to not use locked memory and see what it looks like. So I'm going to quit the debugger. I'm going to restart SQL. Now here's what I'm going to do. This is an undocumented trace flag to force the conventional memory manager. Right here, HT835. So I'm starting up SQL. Now let's go back and run some queries. I'm going to go here and look at this. I'm using the conventional memory model. And notice here, here's my ceiling, and I've got a low amount of memory I'm using. Now, what does it look like over here for locked? This is where it's interesting. We're still using locked pages at a very small level, because if the privilege is set and we're still using conventional, we still can use some locked pages for fixed memory in SQL, not the buffer pool though, okay? And in fact, you can see here, notice that locked is very small. Physical memory is like 415 megabytes. And notice here from our working set, that SQL Server's working set is almost up to that 415 megabytes. So now it is possible to trim the working set of SQL Server. Okay, so let's go back again, and we're going to be very careful here. We're going to attach our debugger again. Okay. Now what we're going to do this time is something a little different. We're going to set a breakpoint on a SQL OS call. And we're going to run the query again. Whoops. Let me do this again here. Okay, so I'm going to break again here. I'm going to this is a little tricky to do this. I'm going to run my query. I'm going to go back to my debugger, and let's see what happens. Okay, it's loading some symbols that it hasn't loaded before, it looks like. But it'll just take a second to load this up. So the reason why it's really tricky to do this is because this is called a lot for a lot of reasons. So let me do this. Let me go here again. Let me hit a breakpoint on this. Okay, let's go here and then go here. Okay. So let's see what this looks like. This is interesting. You'll love this one. This is example of us needing connection memory. Notice here this call, process login read. So if somebody's connecting, we need to allocate that fixed memory for connections. And we're using something, I mentioned this before, called a memory object to do this right here, a memory object. And then we need memory, but we're using the conventional memory model. So if you look over here and scroll this way, you'll see here, this is the call in SQL OS to get conventional memory, and this is the Windows call. Remember I mentioned that earlier, called virtual alloc to get that memory. Let's disable the breakpoints and let the query finish and go look at our accounting now. In fact, it broke because I'll run it again with the debugger. Remember, we're using a conventional memory model, right? So we're going to go back here and we're going to see what it looks like. Okay, now this is interesting. So the target and the ceiling, right, you can see here are near each other, conventional memory model. Now here's what's interesting. The locked pages should be low. Remember, the locked pages are really low, but we're at 4 gigs, so only like 24 meg for locked pages. And in fact, if you go to Task Manager, oh, look at that. You see the difference here for Task Manager? Here's SQL Server. The working set is almost 4 gigabytes. This is why in the conventional memory model, if we had big external memory pressure, that working set could get trimmed really low and cause a major performance problem because SQL doesn't know that memory is no longer in cache. Okay, that's just kind of an interesting example. And again, you have all the different scripts and you have the instructions. If you want to try the debugger yourself on a laptop or something, you could certainly go through this. All right, we'll go back to our presentation here and keep going. But let me pause for a second and see. Actually, let me get back to this right here. Let me pause in a second to see if you have any questions. Feel free to raise your hand or to put something in the chat. Okay, So, okay, is there no, I just want to make sure I understand how to do this. Now, are there no questions because this is, you already know all of this, or because this is too advanced? I can't tell because I'm not physically in a room with you. So feel free for anybody to chime in and tell me whether this is interesting information. I'll just keep going then, because I'm not sure. I wish we could somehow read the facial expressions of avatars. That would be kind of interesting to know. So, all right, let's press on then. We'll have plenty of time to do some other questions for you. So what about some other memory topics that I consider important to SQL Server? Number one is buffer pool. So page life expectancy is a formula that we use, and sometimes people think it's flawed, especially across Newman nodes, but it's still pretty decent. And what that really is giving you is an indication of whether how long a page is expected to live in cache. So you could find some people that debate this if you want to, but for the most part, if page life expectancy is dropping really low, and it used to be high, that's the key point here. If page life expectancy got to a high level and then it dropped really super low, you probably don't have enough memory for your buffer pool, or you're seeing the target go down. So if somebody told me, Bob, I had a high page life expectancy and then it dropped really low, my first question is, did the ceiling drop? Did the target go down? And if they say, no, the target didn't go down, I'm like, you don't have enough buffer pool space, probably. You don't have enough memory for your buffer pool. But if they said that the page life expectancy went down really low and the target went down, I'm like, well, that's memory pressure. You need to go figure out your memory pressure problem before you go look at trying to figure out if you have enough buffer pool space. One other thing that people don't realize is page IO latch weights. That's probably a whole different conversation we could have. But page IO latch weights are an indication, simple indication that we're reading a page from disk. If you see page IO latch weights, it is not an indication of a problem just because you see one. Just the nature of how we do latching to read a page into disk, you must have a page IO latch weight to do that. This becomes a problem if you see a lot of these with a high wait time. That means there's going to be some latency going on from reading pages from disk. And by the way, if you'd like to play around on SQL Server, even though you can't do this in Azure, one way that I do to force pages to be read from disk is run this dbcc command. Drop clean buffers goes through all the buffer pool pages that are not dirty, that have not been written to, and it frees the pages. That way, it forces pages to be read back from disk if they don't exist in cache. Okay, what about NUMA? You probably have servers out today. We're using NUMA nodes. The goal in NUMA is to use local nodes when allocating, not to balance across nodes. So if you think you're looking at memory counters for SQL and you've got 4 NUMA nodes and we're not balancing memory across these nodes, that's expected because we're going to try to go allocate memory on the same node where the worker thread is running for that NUMA node. So the other thing though, because buffer pool itself is shared across all the nodes, local node allocation is not guaranteed of local node access. So we may allocate memory on a worker thread on a given NUMA node because the worker was running there and we had to grow the buffer pool, but the buffer pool shared. So another worker coming along could be on a different node and still need to access that memory, which is considered a remote access. And then other thing to remember here is that some memory that we do, like memory objects, are what we call hot memory that's used across things like hash tables for plan cache. We partition these by NUMA node to ensure that we don't cause collisions or concurrency problems, which, by the way, if that happens, it usually shows up in the form of a spin lock problem. Okay. So what about memory grants? Memory grants are a concept in SQL Server needed for query execution. Usually you see right here, it's fixed memory, not cached, allocated at the start of query execution for things like sorts and hashes. If there's not enough memory grant for your query, according to what is needed when the query runs for, like, say, a sort, we may need to spill to disk. We will start using tempdb as a backing store. Remember that term, backing store. We'll use it as a paging system for the memory we need for the sort. That causes performance problems. But if the grant is too high, because we overestimated the amount of rows we needed to sort pages or something, What you might see is a high number of resource semaphore waits or planned cache eviction, because grants are going to compete with memory for things like plans. Now, a lot of people, when they run into this problem, want to use resource governor, and it's important to know that for very large memory systems, we support a max grant value less than 1% now in 2019. So if you've got like a 4 terabyte server and you need to set that memory grant limit to a low value, it used to be 1% was the lowest you could do, which for 4 terabytes is a lot of memory. So you now can do a floating point number and set it to be a number lower than 1, like a 0.1 or 0.5 or whatever. But really important is this, in 2017 and 19, and in Azure as well, we have memory grant feedback so that after the first execution of a query, we can adjust the grant to avoid these spills and avoid these resource semaphore waits. Now, what about memory leaks? I've had this question come up a lot, like, I think SQL has a memory leak. If SQL Server has a leak in its own code, like in a memory manager code, or in say like code that needs memory for fixed memory, the behavior is out of memory errors in the error log or message 701 errors. That's a leak within SQL Server because let's give an example. Maybe we have a leak in the plan cache code. So we allocate memory for plan cache, but we don't give it back up ever, even when there's pressure. So what eventually happens is SQL uses all its memory, and then eventually you'll get out of memory errors. Now, by the way, one quick tip for those is go look at the clerks. Look at your memory clerks to find out which clerk is consuming the most memory other than the caches, other than buffer pool, and you might find out the source of the leak. There's also some very advanced techniques with X events you could use to find out that problem. Now, what about private bytes, which again, remember, private bytes is the memory we're allocating. And by the way, private bytes is inclusive of locked pages. What if that gets really high, bigger than SQL Server's total memory use? Remember the total memory being used or the committed? If private byte starts leaking, there must be some other code, not in SQL Server, but like in a DLL or something, that is running the SQL process space that's causing that leak. I've seen that before. In the old days, I used to see it with extended stored procedures, but there are other ways DLLs can get loaded that could be causing that problem. Okay. Let's talk about plan cache eviction and why this is important. So first of all, buffer pool gets the majority of memory, even bigger than the plan cache. It's important, right, for both of them actually. But you certainly want, in most cases, your buffer pool, and you would expect the buffer pool to require more memory than your plan cache, right? But it's a major performance impact when plan cache eviction occurs, and let's talk about why. So first of all, if there's memory pressure going on, like in the examples we talked about where we lowered the target or we're hitting the target, so it could be hitting the target or external pressure or large memory grants. Memory grants can be a competing factor because we're not going to allow memory grants and plan cache and compile memory and all this stuff to use as much memory as they want. They compete with each other. When that happens, we have a concept called a clock, okay? And you can see this clock in the form of certain DMVs. And I've got a pointer here in the deck when you see it to go click to read more about this. So what happens is this. When the clock hand moves, we start marking these plans for eviction. And then after a certain number of passes from the clock, we'll actually do the eviction itself. So it's a way of us not immediately getting rid of things, but using a clock sweep algorithm to decide, hey, so many times I've had to come through here and had problems with this, with pressure, I may need to remove a plan from cache. So that's pressure. Could be internal pressure, could be external pressure, or it could be large grants. Now, also though, there are cache cap limits. We do not allow in SQL Server the plan cache to grow unlimited. Okay, there's certain limits. And the plan cache limits vary based on size, the type, number of entries. There could be something called a cache war. That's a term I invented, where other types of caches are also growing and they're all competing for these limits. So there's another clock hand for cache limits called an internal clock hand. Again, the DMVs can show you this, right? So we will use different clocks to represent how to evict plans from cache. It's important for you to know that because if you're seeing unexpected plan cache eviction, you need to know which one of these problems is happening here. Is it memory pressure Or is it a limit that I'm hitting just with a pure number of plans? Maybe you've got a scenario where you're using too much plan cache with ad hoc plans. So these clock hands through DMVs can tell you which one am I running into, so you can know how to go figure out the problem. Now, it could be, though, that you might have caused the problem. You're like, how do I cause the problem? Well, you could have run one of these commands. These type of commands that you run can cause us to evict plan cache. It has nothing to do with the clock hands themselves. And just keep in mind, you need to be smart with what you cache. I just mentioned you may have used too many ad hoc queries that are getting cached when you need to parameterize these queries or perhaps use stored procedures. Okay, let's talk a little bit about Linux and then talk about Azure as we finish up today. We have about 9 minutes left in our presentation. So, SQL Server on Linux. The engine of SQL Server is the SQL Server engine from Windows running on Linux, okay? So the engine behavior I've described right now is pretty much all the same. The only difference is this: the operating system behind the scenes that causes memory pressure or signals memory pressure is different because it's running Linux. So in fact, we have something called a memory limit MB configuration value that is going to provide the maximum possible memory to SQL. When you go look at the, let's say you set max server memory to 0. Well, max server memory to 0 means the default is 80% of physical in Linux. You can change it though with this memory limit MB counter. Lock pages doesn't matter in Linux. There is no concept called lock pages, so we don't even set that up at all. But there is working set trim problems. Linux can page memory to what's called a swap file in Linux. And in fact, Linux has a different behavior called the out of memory killer, OOM killer, where it can kill processes because of huge memory pressure going on. So if you see that, that's a unique behavior to Linux. We have kernel tuning best practices that you can see in the documentation to help avoid those scenarios. What about containers? Containers are just isolated processes, okay? So, but there is ways to take container runtimes, like with Docker, and configure the maximum memory for containers. So be careful if that's the case, because by default, containers get access to all the memory in a virtual machine or in a bare metal server. There is no equal division of memory for containers. That's not how it works. They're just processes. They get access to everything. You can control that, though, through the container runtime, but I don't recommend you do that. I recommend if you're going to control container memory, you use max server memory to do that, or memory limit MB. Think of containers, multiple containers, as multi-instances of SQL and treat the configuration of SQL accordingly, okay? Now, what about Kubernetes? This is an interesting one. Kubernetes has its own system for memory pressure within Kubernetes nodes. And we've seen people not configure memory nodes in Kubernetes enough to account for SQL. SQL is not aware of any memory eviction policies. We've seen people configure Kubernetes nodes too low, and then the Kubernetes will come along and evict the SQL pod and move it to a different node. And SQL is not aware of those policies. So you need to make sure you accordingly give enough memory to the nodes. Think of the node as being like a VM. Give it enough memory for any containers that are running for SQL in those pods. Let's finish today, the last 5 minutes, talking about Azure. So first of all, Azure VMs, think of it as the same as SQL Server today. We have memory optimized sizes in Azure VM where you have high CPU to memory ratios, but you configure inside the VM just like SQL. Use lock pages, do all the things we just talked about, because it is a full virtual machine just like SQL Server today. But what about managed instance? This is a little different. It's platform as a service. So memory is going to be limited per vCore. And in fact, each vCore you set up is going to give you additional memory from an overall possible memory. Think of your fixed memory limit as being like the available physical memory of a VM for your managed instance. In-memory LTP does come with business critical, but we limit that memory just like we limit the memory inside SQL Server, and we document what those limits look like. And then you don't know the virtual machines that power these managed instances. So we may not give you the entire physical memory of the VM itself, so we can manage all these properly across the clusters. So memory limits are enforced by something called the Windows job object, and I'll show you that in a second. What about Azure SQL database? With the vCore model, we scale your memory limit. the more cores you get, the more memory you get on a fixed basis. So X number of cores give you X amount of memory. And we also enforce these memory limits with Windows job objects. Now you may wonder, like, how much memory can I get? Well, look at that. The business critical M series hardware can give up to 4 terabytes of memory for your Azure SQL database. Just like managed instance, in-memory LTP is only with business critical. And then there's something called serverless that you may not have seen before. And we have min and max memory limits. Think of the target. That target can become a factor. And if you don't use your serverless because you're pausing compute, we may lower the target on purpose to give up resources because, again, you're running in a serverless environment. And then hyperscale is interesting. The same memory limits apply for general purpose, but it has a series of caches. There's a series of very smart caches. So even though you think you're not, you may be limited by memory from the primary replica of a hyperscale, because of this cache system, your performance can be very high for very large database systems. So let's briefly take a look at something I've got set up here. So in Azure, I've got a VM. Let me get to that right here. I've got a VM set up here in Azure, and I'm connected to a managed instance. So just like in SQL Server, you have things like clerks. So let's see, here is an example of clerks. I'm not even really using much memory right here, but the same clerk concept applies. It's just a SQL Server instance. But there's a couple of things I want you to notice. Look at OS sysinfo. This is the target we get here. Notice here is the committed target that we get. Whoops. Run that again. So here is our ceiling. Okay, sorry, zoom it. I did not set up zoom it properly on this machine, but here's our committed target right here. This is around like 7 gig that we set up. But notice this is interesting. I'm gonna go over here and look at the error log. You get to look at the error log in a managed instance, okay? And in here, notice that we think we have like, well, actually that's like 8.1 gig of memory available, 81 gig, or 89 gig. So the VM that's this running under has almost like 89 gig available. But if you go over here to look at this query, which is called, this is a special query for Azure, you can see here that the limit is a lot lower. And here's the job object to kind of show it to you. If I run the job object, it shows you here that I'm only giving you about 82 gig, right? So I want you to be aware that if you start looking at the error log, which a lot of people do, and say, hey, that's the available memory here. I've got max server memory set to 0. We may use memory objects to limit that. And again, that's published. If you go into the documentation here, I think I've got that. Yeah, right here. If you look at the documentation, these are resource limits documented for Azure. Notice here we say you get about 5.1 gig per vCore that you set up. So again, if you want more memory up to the max that we can give you, you're going to add more cores. It kind of makes sense. The more cores you need, the more memory we think you need in your environment. So that's just a brief look of what it looks like in Azure. One thing I did want to show you though, in your normal portal for Azure, you don't get information about memory. Here's CPU utilization, but there's a new service that we've added called SQL Insights. SQL Insights is going to feel like a perfmon. You see it right here? You get information about your managed instance that looks like a perfmon, and I can go here and look at the clerks from a visualization point of view, just like I can do this with DMV queries. So check out SQL Insights. It's almost like having perfmon in the cloud for you to look at your managed instance. Okay, we are right at the end of our time today. Let's finish off here and look at some resources. All the decks are here. All the demos are on a GitHub repo. If you want to learn more at Azure, get free training here. Free training from the Azure Sandbox. This is free training also for SQL Server. I've got some articles and documents for you to take a look about with some more architecture. Or if you're an avid reader and if you've not seen some of the books I've written about Linux, SQL 19, and Azure, please feel free to check those out as well. I'm going to leave this slide up here as we finish today so you can look at it. But remember, go here to this site to get the slide deck. If you have any questions at all, my email is bobward, BOBWARD, @Microsoft.com. However, also, I am fixing to leave here as a speaker, and I'm going to go into the auditorium to be joined by my colleague Buck Woody for a general Q&A. So you're also welcome to come answer questions there. I hope you enjoyed the presentation today and you found it was useful. Again, this is a very advanced topic, so I know it's a lot to consume, but I hope it also helped enrich your knowledge of how SQL Server works behind the scenes and how you need to understand more about how memory works so you can effectively manage and optimize your SQL Server. Thanks again so much for coming to today's presentation.